Okay, we're happy to have Andreassen from Berkeley. He's going to tell us about JUNIPR, which involves unsupervised machine learning, or just learning.
All right, well, thank you for inviting me. It's very great to be here. We're not so physically far away, so it's good to meet everyone who's here. So today I'm going to tell you about some of my recent work that I've done with alleviates and Chris Fry, who work for ASI Data Science in London, and Matt Schwartz at Harvard. So I'm going to talk about basically the application of machine learning to jet physics at the LHC. So I'm going to start out with just sort of like a pretty broad introduction to make sure everyone's on the same page. Jets, and talk about jet classification. And I want to use jet clustering trees sort of in the construction of this thing called JUNIPR. So I'm going to talk to you a little bit more about that. And then the neural network architecture I'm going to be using is called recurrent neural networks. So I'm going to be introducing what that is. And I'll tell you about this paper that we wrote in April or May 2018. And feel free to interrupt me at any time. I'm happy to address questions as they come up. So broadly, what is a jet? So let's say you take E plus E minus collider, shoot at each other, and a little bang happens. Out comes a quark-antiquark pair. The quarks will radiate off, say, photons or gluons, and eventually they'll decay and decay and decay until they form into like more stable hadrons. And these are things you actually see in your detector. So at short time scales, there's a hard collision. On the long time scale, there's these sort of soft and collinear emissions, and these quarks and gluons hadronize. And these sort of collections you see, so one collection up here and one collection you see down there, these collections are these collimated sets of events. That's what we refer to as a jet. We have two jets here. So you might ask, why are these jets important? So they're inherently interesting emergent phenomena of QCD. But also very useful in searches for new physics. And if you want to study, say, precision standard model measurements, like the Higgs decay, they're also very important. So let's understand that in the case of the Higgs decay. So here's the branching modes for Higgs. 61% of the time goes to quarks, 9% to gluons, 21% to Ws, taus and Zs there. But whenever I have quarks and gluons, as I saw in this previous page, they're really evolving to jets. And we group those together. So when I have a W boson, only 6% of the time if I have W boson pair, only 6% of the time do I only get leptons out. 94% of the time I'm going to have at least one jet involved. So that's also jets. Same story if you have taus and Zs, they also form into jets. So really, for the Higgs decay modes, only 2% of the time do I not have any jets involved. Otherwise, at least one jet. So if I want to try to understand these different branching modes, understanding what these jets are and what was the underlying sort of hard particle that created them is crucial. So the thing people often talk about in jet physics is simulating these are light quarks versus gluon jets. So if I have a quark traveling here, it's going to radiate off soft gluons and collinear gluons. And here's a gluon that is also radiating, this is colored. And if you look at the branching probability for like these, so here you see this, the soft singularity and the collinear singularity. There's a color factor that's sitting in front of here. And the ratio for the gluons to the quarks is 9/4. So on average, gluon jets are going to be fatter, they're going to be more massive, going to contain more particles, but this is only on average. So if I event by event, distinguishing if I see a jet in my detector, was this a quark or is this a gluon jet, is really, really hard. But understanding this difference is important in understanding the new physics, but there's a fundamental question in QCD, how do you distinguish these two? And if you look at sort of progress in jet physics, you can sort of, one benchmark people have used this is sort of how well can you distinguish quark versus gluons. And especially in the sort of machine learning for jet physics community, this has been a very important benchmark people are using. So if you want to do jet discrimination, the sort of traditional way, which has been done for a long, long time, is to define some sort of set of like expert observables. And then you can also combine the multiple different observables to try to get like the best discrimination power. So here's a sort of semi-recent paper out of Harvard, where they sort of, at least in one section of their paper, they just list all the different kinds of like observables they were considering. So here's particle track, multiplicity, PT average, the mass of different subjets. There's things called end subjetiness. There's like jet mass, jet shapes, girth. There's a bunch of different things. And then my point is not for you to like think about what all these things mean. Just your impression should be there's lots of different things people have thought about, sort of with different like theory inputs. They've constructed these observables to try to use them to distinguish quarks and gluons, and also other things, not just that. So the question is, can we do jet discrimination with machine learning? So machine learning is really, really great at classifying really high-dimensional input data. So here's a little cartoon. So here is a picture of a little dog in a little basket. And a neural network is just a set of nodes, sort of separated into the different layers. And every node in this layer is connected to every node here is connected to this node, and there's some weights connecting each of them. And if the sort of stimulus from the sum of these weighted nodes into that one is high enough above some threshold, this neuron will fire and sort of propagate the signal forward. So the sort of task of machine learning is constructing some sort of architecture of these artificial neurons, come up with some different sort of activation functions, how these neurons should fire. And then essentially you just have to start with some sort of random weights connecting different neurons. You have to train and tune these weights such that it performs that sort of classification test that you want. In this case, you feed it in this picture, and out comes this is a dog, not a cat. So the question is, can this sort of framework, machine learning, be used to automate jet classification? So machine learning for jets is a really rapidly growing field of research. So here's a plot that Ben Nachman made for this youth conference last summer. So here's time on the horizontal axis and number of papers with the word jets and deep neural network in it. So it seems like it's more or less in like an exponential growth in papers. So there's already been a review as of September 2017. There was a review paper on the state of machine learning in jet physics. There's been 2 dedicated machine learning for jets conferences, one in 2017 and one in 2018. So we live out here somewhere now. So it's really growing, lots of exciting new ideas and work happening. So just to give you an impression of the sort of simplest idea in which you can use machine learning for jet discrimination, is the use of jet images. There's a bunch of references if someone's interested. So imagine that you have, so your detector, okay, let's see, you have some event happening and you get 2 jets coming out. Say you have like up here is a boost of W. You take what do you see in your calorimeter, and you plot it in a 2D plane with the pseudo-rapidity versus the azimuthal angle, and you read out the energy deposited in all the different cells in your calorimeter. And the essential idea is going to be now treat this as an image and try to do the same sort of, is this a cat or a dog kind of classification. So in practice, how this is done is, here's one example of the way which can be done. So again, you have your sort of beam here, 2 particles colliding, and some sort of energy is deposited into your calorimeter. You can think of, so if you have a picture, you have 3 different channels. You have the red, the green, and the blue. So similarly, from this paper, they sort of into the red color channel, they fed the transfer momentum of the charged particles. Into the green channel, they fed the transfer momentum of the neutral particles. And into the blue channel, they fed the charged particle multiplicity. So they fed that in to the network, get these 3 different layers for an event. And then there's this sort of network architecture called convolutional neural networks, which the details aren't really that important, but there's some sort of network architecture in which you analyze these pictures, and then the same sort of architecture that Google uses when you search for cute cats on the internet. You feed that through, and then you ask for a classification. Is this a cork or a gluon? So you might ask, how well does this actually work? Here's a plot from their paper. So all these dashed lines, I hope you can see them here, are these more traditional observables that sort of you have from the theory of girth, charge particle multiplicity. These kinds of plots I call a rocket curve. So the way you read them is if I have some sample at the LHC, and I want, from that sample, I want to keep 80% of my quarks, how many of the gluons am I rejecting? So if I want 80% quark efficiency, I go up here and I say, looking at the best curve, I go over and I say, okay, if I get 80% quark efficiency, I get about 80% of the quarks rejected. So in my sample, if I make a sort of copy in this value, I will keep 80% of my quarks, but I also have 20% gluons that I can't get out. So the only dashed ones are these theory inputs, observables. And you can also combine those in this like a boost decision tree, where you get this sort of solid blue line. That's like the third best curve here. But you can use these deep convolutional neural networks, as I described before. Here's the sort of grayscale where there's average different colors, and the black one is just these 3 different color channels. You can see that these machine learning techniques do better than what I could do with these traditional observables.
What's the best traditional one?
I think it's this N95, which I honestly don't remember the exact definition of that. I think that's their best one here. But generally, if you're trying to distinguish quarks and gluons, multiplicity is a pretty good one. Also, girth, I guess girth is not doing that well. But I think
Which is the multiplicity curve on there?
It's a bit hard to see with such a color. Maybe that is the best. I can see from my computer monitor. Actually, yeah. So the best one here is charge particle multiplicity. That's the best one. So, if you want to do jet discrimination with machine learning, here's some proof that it might work pretty well. And it's sort of outperforming more theory observables. But if you're a theoretical physicist and you see these things, you can sort of ask, or at least the questions I ask myself, is there some way for us to understand what is the machine learned to get much better performance discriminating quarks and gluons than what sort of observables we already have? And is there some way for us to try to step towards extracting that? And if you only care about getting the optimal performance, I just really need as much quarks as I can while throwing out as many gluons as I can, you might not care so much about these questions. But if you really just want to understand what distinguishes the quark jet from the gluon jet, that's sort of what we're probing. We're not quite there. I shouldn't let you think that we're there, but you're trying to step towards that. So the sort of motivation for JUNIPR, and I'll get to what that stands for later, is can we really understand jets better using machine learning? And sort of broadly, our idea is we're going to have some sort of neural network learn about jets and something about the evolution of jets. And then we're going to try to peek inside this, what we call the black box, and try to see what it's doing. And this is notoriously difficult. So the sort of strategy we're going to take is we're going to choose our network architecture in as clever way as we can. We're going to structure it around clustering tree, if like inspired by QCD shower. We're still going to let it be general enough. We're not going to restrict it to only learn QCD because there could be something that's non-QCD about a jet. So we want it to still be flexible enough. And as I'll get to in a moment, we're going to build this recurrent neural network around this clustering tree. I'm going to see how this kind of structure might take us towards interpreting what is happening at the different layers in our network. Got any questions so far? All right, so then I'm going to be using these clustering trees. Let's just take a step back and define them properly. So you can find there are different ways of defining clustering algorithms. One is just by using gentle angular ordering. So if I have some detector and some momenta in my detector, I'm going to sequentially cluster pairs of momenta with the smallest opening angle. So if I look at my detector, I locate the two which have the smallest opening angle, and I'm going to merge them together. With that operation, I'm going to define a clustering tree. So here I'm labeling the momenta P1 through P6, and I merged 4 and 5. Now I locate the next nearest, the next pairs which have the smallest angles. Now it's between the sum of these two and P6, and I'm merging those together. Next closest pairs is 2 and 3, merge those together. Next, 1 with 2 and 3, and then lastly, take these two. If I have multiple jets, so this is just really like a small outcut of the whole detector. Typically you have multiple clusters, and you have some sort of length scale that you define where you put a cutoff as to when you stop merging together. So with a set of particles I defined in the detector, I have this deterministic algorithm, just here by angular ordering, that gives me this sort of unique tree. And often I'm going to now change my word. I'm not going to talk about the clustering, and we're going to talk about the declustering or the showering. So I'm going to be thinking about starting with the sort of total jet momenta and seeing how we go from the total jet momenta and how that the first splitting, the second splitting, third splitting, fourth, fifth, and then here I stopped. I'm going to be talking about this sort of showering of some sort of hard particle. Yes?
I think like this is exactly what you're doing with the KT algorithm, but conventionally.
So, yeah, so KT is just a different choice of the clustering algorithm. So there's just like a different measure of which things are the closest. So there's just a different distance measure on this space.
So in essence, like you can build different neural networks based on different algorithms, like Aachen, anti-KT, you can implement
Yep.
each one.
So you can choose whichever algorithm you want, and we looked at, this is called Cambridge-Aachen, which is angular ordering. There's KT, which is very much used. There's also anti-KT, and we did implement this for anti-KT, and I can get back to that at the end if you're interested. So if we have a clustering algorithm, we automatically get this kind of tree structure. Yeah. So let's just do a basic introduction to what a recurrent neural network is. So recurrent neural networks is a sort of network architecture that's used to naturally model sequential evolution, for example, language. And the great thing about these is that they allow for indeterminate number of time steps, while some other neural network architectures, you've taken a picture which is like a fixed 124 by 124 pixels. So I don't know how many particles I'm going to have in my jet. So having this arbitrarily length is great. So all of you have a little recurrent neural network in your smartphone. So when you're texting on your phone, and you typed in at the end of your phone might list 3 suggestions for what the next word might be: month, day, week. So what is really happening here is that there's a little recurrent neural network that is coming up with the predictions for the next word. So the way it works is that your sentence is a sequence. And for every element in your sequence, so here I'm at sort of time step t, there's some what's called a hidden representation. There's some sort of embedding of your sentence, whatever you've written in your sentence so far. And then in your dictionary, for every word in your dictionary, there's this, the recurrent neural network predicts the probability for every word in your dictionary. So for the top 3 words in your dictionary, it's just going to display them for you, thinking that's like the most likely thing you'll type next. So in terms of a diagram, here's a diagram of the recurrent neural network. Think of there's a sentence here that's being fed in this hidden representation HFT. So I had a prediction for my words at time t. So let's say that was day. So when you actually type in the word day here, you take the hidden representation at the previous time step, sort of the embedding of what has happened so far. You now say, I'm going to add the word day. So feed in hidden representation, and the new word gives you an updated version of your hidden representation. So you're always taking in the sort of previous time step hidden representation plus the new word to give you a new embedding at this time step. And that gives you the next prediction at time step t plus 1.
So is the idea that this is supposed to get better the more information you give it, or is it really just kind of always supposed to be predicting the next step without knowing what came before?
So it is always just predicting the next word.
Yeah, but is it supposed to get smarter? Like the more you give it, it's supposed to take into account everything that came before.
Everything that came before. In like typically, I think they're implemented as like in that sentence. So when you put a period, I think it typically like forgets. Like it doesn't. It sort of resets.
Yeah, okay.
But yeah, so like as you, like if you just give me a sentence, and I sort of like just as a human think about that sentence, there's a sort of probably like a limited number of like word, like the 10th word. There's only like so many like reasonable guesses I can have for that.
Right.
But if you give me like one word, and I'm going to predict like the next one, it's just like sort of two. So you give me a 1-word sentence. Like there's so many more like possibilities. So I'm not sure if that's answering your question, but there's just like a much, as the sentences go longer, there's just much less wiggle room for like reasonable sentences. So in terms of a neural network, so I have some sort of parameters that is sort of describing this hidden representation. And I have to sort of, and there's some parameters that sort of takes, like adapting how to take in the new word, and how to sort of merge that with this hidden representation. But those like number of parameters I have are the same for every time step. So typically we just like draw this whole diagram as this sort of wrapped up diagram. So you think about it, there's some word that's being fed into the hidden representation, and this loop back with a box on it just means take the hidden representation from the previous step. So box just means time step -1. For every time step, you get a prediction for a new word. So the analogy I'm going to be making is for jet evolution, the analog of a sentence is a jet, and the analog of the next word is just index splitting. So here we had this clustering tree. So it was from the final set particles. I get a unique tree, and the tree defines a sequence. So there's this splitting, that splitting, third, fourth, fifth, and then an ending. So that's the sequence I'm going to be modeling. So JUNIPR stands for Jets Using Unsupervised Interpretable Probabilistic Models. So that's a lot of words. We'll get into all of them. We'll start with what the probabilistic models mean. Well, that's just, so here we have a little logo of JUNIPR, so a little JUNIPR branch, and it kind of looks like a little jet. So a piece of sort of the particles being decayed out. So we think that's pretty cute. So what is the probabilistic models for jets? So again, if you have some hard events at the LHC, there's some sort of unobservable QCD evolution, and then there's the sort of moments that you measure in your detector. So we can't really observe this. What we want JUNIPR to do is that we have a probabilistic model. We really want to model the probability distribution over having this set of final set momenta. The JUNIPR, the output is P of jets of a collection of form momenta. So from Q, is there a question?
Yeah, I guess I haven't really understood what you're doing yet. I mean, as you said, QCD plus possibly some modeling predicts this probability, but you are now, maybe you're going to explain better Juniper is actually gonna do? I guess I just haven't gotten what is Juniper doing?
Yeah, so there are many steps there. I guess so what do you mean that?
Well, I guess I didn't even get what the bottom line is, of what Juniper does.
So, what we're going to do is going to be modeling these sort of probability distributions. So if you have, say, quark jets at some energy, what is the probabilities over some of it having like some set of final set momentum? And I'm going to be using that for discrimination. And by doing discrimination and like building up the model which I'm doing, I'm going to sort of like peek inside and understand like why is my machine learning, why is my machine thinking that this is more likely to be quark versus the gluon?
So at one level, Juniper is a machine learning framework for example, discriminating quark and gluon jets, but
Yep.
it's designed in such a way that you can look inside and hopefully learn more about why, how it's doing what it's doing.
Exactly.
That's the idea.
There's also some other things we'll get to, but that's the core idea that I'm trying to get across.
So you're allowing for an arbitrary number n, as well as arbitrary momentum, or?
Yeah, essentially. In practice, there's a cutoff, but the cutoff can be arbitrarily high. So from QCD, I
But
get
you're inputting a type of jet or not?
I'm inputting a type of jet.
So if you give me if you say it's a gluon jet, then you get just P jet. If you say it's a quark jet, you get a different P jet.
So in practice, I'm going to have, if you give me a sample of quark jets and a sample of gluon jets, I'm going to separately model them.
Mhm.
And then I'm going to be comparing like the probabilities of each. If I sort of give you a Mr. Jet, I can compare give me a Mr. Jet, and I can say like, okay, feed that through the quark model, feed that through the gluon model, and I can look at the probabilities that's predicting and try to like make a quantitative statement of like how likely is this to be a quark versus a gluon.
Something I should have asked before, but back when you showed that plot, whatever it was called, the one that tells you the efficiencies and the fake rate, you had those curves. I was just wondering if any of the machine learning ones have actually been, are those data or are those Monte Carlo?
This is all Monte Carlo. That is the status of like most of these sort of theory things. Observables are also typically on Monte Carlo. But there are people working on getting this on real data. And I'm happy to talk about that. I haven't worked on it myself, but there are ways from the colleagues
It's
to.
really hard, it's not easy to validate that, I guess.
It is hard to validate, indeed.
Okay.
But we can talk about it afterwards if you're interested. So I was just going to say that this kind of prediction of the final segment, like getting the sort of like probability density of some sort of specific set of final segment, it's not something it's easy to get from just QCD. QCD you can predict like what's the probability of having sort of like a 1-to-2 splitting, and that's what like your Monte Carlo generators are doing. But then you get into hadronization, and there's like all sorts of complications that happen. So producing a sort of estimate of P-jet from like QCD is really, really hard. So that's what we're trying to do.
I'm afraid I'm going to ask my question again. Sorry. So because the way I understand the only kind of neural network I even vaguely, machine learning that I even vaguely understand is this traditional thing where at the very end it gives you a weight of which output you want. Is it a number digit 1 through 9, 0 through 9, or is it a quark or a gluon jet? Here you're saying that you wanted to output a probability distribution.
Yeah.
Now, what does that in practice mean?
So this is the unsupervised part of the title. So typically, if you have what's called supervised machine learning, say like you're trying to classify these like n-list digits, like there's some collection of handwritten digits, and you try to like you feed one in, you get out like this, which category does this fall into? 0, 1 through 3, all the way up to 9.
Right.
So then typically you have a data set. You have say in your data set, like all your examples are labeled. You learn so you feed it through and you get out like what the probabilities are for different ones, and you know what the right answer was, and you can try to like change the weights such that like you maximize that. So if you have what's called unsupervised machine learning, you're really just trying to model the sort of structure of your data. You're just trying to learn like what the sort of distributions are of my data, but there's no right or wrong label. I don't have like a true or false label to the probability of this was, I don't know, 0.009. Probability of this was 0.00001. I don't have labels here.
So it decides, the machine learning is going to decide, well, why don't you go on? Because
Yeah,
I still don't understand. Maybe we
please
can-
ask me
I have a
again
feeling
later,
we
but
get
this is
to
a
the-
conceptual difference from what most machine learning like talks you here, because they're typically supervised. This is an unsupervised machine learning algorithm, and we are modeling these probability distributions. But I'll talk more about that modeling as we go along. So, but please ask me more again. Any more questions?
We should just go second bullet.
So yeah, so given some sort of training data, JUNIPR learns these probability distributions over these things. That is the bottom line. So if I have, say, 30 particles in my dip, this distribution, probability distribution, is going to be something like 100-dimensional. If I have 3 degrees of freedom per particle. That's very, very complicated. That's a 5-dimensional space. So I'm going to make it a lot easier. I'm going to build my network around this sort of clustering tree. So if I take my final state momentum and I'd like to find a sequence, now I only have to model. I can factor my total probability into products of probabilities per time step. So I just have to model the probability of like time step 1 times a 2, 3, and 4. And at every time step, I just have one particle branching into 2. So there's a 4-dimensional probability distribution I have to model. So instead of modeling just the final sort of complete state at all in one go, there's 1-dimensional. And breaking it into time step, each one is just 4-dimensional. So by using this sort of clustering tree, which is sort of inspired by like the QCD shower, modeling it this way, like it increases the efficiency and it reduces the complexity. And with this factorization, I'm modeling probability distribution per time step. So this also leads to some amount of interpretability because I can look at the probabilities per time step. So I have more control over what's actually going on.
In QCD, though, is this any kind of approximation? Because in QCD, you always have a 1 to 2 type structure, right? Each step.
So if I take QCD without patternization, so let's say I take Monte Carlo generator and I create some sort of event, but I don't patternize it, I would expect that something like if I choose my clustering algorithm to be like KT or Kim-Jokin, I do expect that there's some sort of resemblance, like it's not necessarily 1-to-1, but there's some resemblance to the tree structure to what actually sort of happened in the Monte Carlo.
Yeah, but
But
I see
if
what
I
you're
had-
saying is patternization, you could get
Sudden.
more than 2 from a single branch. Yeah.
So there's definitely like complications like that, but I should emphasize that since patternization is so complicated, I'm not really trying to model like what's happening in the Monte Carlo generator. And also what's happening in the Monte Carlo generator is not necessarily what nature does.
Yeah.
So all I'm doing is I'm looking at my final state particles, like what I actually can get access at the LHC, and I'm artificially constructing this sequence with this clustering tree, sort of assuming that this is some sort of efficient encoding of like all the information in my jet. I could just contrast that with, let me choose a completely ridiculous clustering algorithm that has nothing to do with nature. The order in which like the data is sort of organized is presumably more scrambled and hard. Like there's more difficult correlations to learn. So choosing a weird clustering algorithm will not make it less complex. But like if I choose a sort of reasonable looking clustering algorithm, I'm hoping that will sort of make it efficient and be simple and sort of. But I'm not trying to model like what's happening inside of a Monte Carlo generator.
So of course, this won't take into account final state interactions or anything like that,
Sure.
right? So you're really relying on you're having a reasonable first description of if there were strong gluon exchanges between final state
Yeah,
jets or something, it could be way off, but maybe.
yeah. But that is something that's not like if I'm just trying to do any other traditional approach also, I'm just give me a jet, you can measure
I understand.
all like sorts of like girth and mass and multiplicity. You still have like no control over those, so they're not like yeah. But it's definitely a complication.
Usage step is 4 dimensions.
So here I say I start with here I have one for momentum, and then here I have 2 at this time step. So there's 4 degrees of freedom.
Okay.
I'm going from one to the other. So let's be precise about exactly how we're doing this factorization. So PJet is factored into time steps. So if I'm at a given time step, so I'm going to look at this time step here displayed. I'm conditioning my probability at that time step. I have the set of momenta beforehand, this red line. And I'm modeling the probability of having this set of momenta after that splitting happened. So it's probability of having this set given I have these set of time step before. That's the general factorization that I'm doing. But I can do a further simplification, as I said, because here I am, only one of these momenta are actually splitting. All the other ones are left untouched. So there's the language I'm going to be using is I have one mother decaying into 2 daughters. So it's labeled so like M and D here. So if I'm at a given time step, so if I'm modeling this shower, like sort of a few things can happen. So this could be the end of my shower. Like this could be this end point. So I have to decide, okay, model like what is the probability that my shower ended at this time. So I have this P of end of did not end or did end. If it did not end, I have to model which of these mother candidates is the one that actually split next. So I have P of mother, but I have some index over these mothers. And given that this mother is the one that branched, I have to model like what is the splitting of here? What is the probabilities of her creating like those 2 daughters? So the way I'm factoring by my time step is going to be at its given time step, should I end now or not? If I shouldn't end, which of my candidate mothers is the one that splits? Given the mother, how does it split? So that's the sort of like factorization that I'm doing. And here I just wrote down all the formata that was at the previous time step. Here I replaced that sort of conditional probability on like this H. And H here just represents like what has happened in my jet evolution so far, which is really the same as like what are the momenta at this previous time, like what are these momenta. And that's going to be this hidden representation of my recurrent neural network that I mentioned earlier.
So somehow, in essence, you would imagine feeding in jets to this thing, and it would come up with the best model of this type that would describe the data.
I'm maximizing the sort of probability, I'm learning the probability distribution over how, like when should I end, which particle should split, and how should they split.
But I think this is opposite what you're saying. I mean, he's trying to predict what the probabilities of different configurations are at the end.
Yes.
Whereas if you have an N, I don't see how this will help you to work back.
I'm not sure if I understand.
So if you have a certain number of particles with certain momenta that
Yes.
you see, will this allow you to work back and say what are the probabilities of different steps in order to get to that point?
Yes. So, you give me a set of momenta. I start at this last time step. Say here I have 1, 2, 3, 4, 5, 6 particles that you gave me. I construct this tree, and then my model, this JUNIPR model, then I can model I sort of start from this end, and I say I start with some seed momentum, and then I have what JUNIPR gives me is the calculated probability per time step. So I just insert what I said, what happened in this first time step, and I get the probability of that happening. Then I update my hidden representation thing. This is what happened in the previous time step. Now model the probability distributions of the next time step. So I get a probability of this node. And then I step through my whole sequence. So I can look at see what the probabilities are for all the intermediate time steps here. Does that answer your question?
I'm not sure, because there's no way of guaranteeing if you start with a certain initial momentum that you're going to end up with the state that you see in the end, right?
So I am not, so you give me a fixed set of momenta here, and I
Right.
construct a tree, and that's a unique tree. So when I've drawn the tree, I've already fixed, so I know exactly how each of the branchings happen. Like, I can label them, when I'm clustering, I label these edges and vertices with like what the momenta are at each time step.
Yeah, but given...
And then,
given
but then I'm
certain-
not sampling. When I walk the other way, I'm not sampling. I always know exactly what those momenta are, and I'm just evaluating on those values happening.
But then you would have a low probability of ending up with the particular final state that you see. Is that not right?
Yes, like that probability is small. Sorry, well, the probability I'm modeling of ending up at one particular final state is small. But when I'm evaluating when I'm stepping through the tree and evaluating, I have a fixed tree, and I'm always evaluating that one
Right,
tree.
I understand.
Yeah.
So
But the values that will come out here at the end are going to be small. I'll get back to that.
okay.
Yeah.
At the end, do you still have full momentum, or you don't only use free momentum?
And I use full momenta everywhere.
Okay. Even though maybe you may not be able to observe.
Yeah. There's some you start with always being four momenta, and I'm conserving four momenta at each vertex. So these intermediate states are not on shell necessarily. These are just sort of artificially added up momenta and some artificial like masses. But this okay. Let's move on. Please ask more questions. But what I was going to say was that this sort of factorization is without any loss of generality, assuming that this conditional this representation of the jet actually is encoding what is going on. So just to summary so far, JUNIPR computes the probability density of a jet. It does it as a product over time steps in a clustering tree, and each time step is decomposed into three parts: P and P mother and P branch. So, if I actually want to implement this in an RNN, I have to do two things. First, I have to do the encoding of the jet structure. I have to encode this hidden representation, encoding what has happened up to some time step. And once I have that encoding, I have to use that to make these predictions P and P mother and P branch. But still, in step one, doing the encoding. So I said before that the analog of a jet is a sentence, and the analog of the next word is the next splitting. So I said for the case of the words, I'm just always updating my hidden representation with adding in what is the latest word I add into my sentence. Always just what is the latest word. So here I'm just feeding in instead of adding the latest word, I'm just feeding in what are the newest two pairs of daughters that I added in. So feed in the four momenta of those two latest two daughters. I have some hidden representation. I see what was the latest two daughters that I added, and I merge those two together. And this sort of stepping through the tree builds this hidden representation. And compactly, I'm going to encode it this way. So this is RNN, recurrent neural network. That's this hidden representation. That's updated the daughters and the hidden representation of the previous next step.
Of course, you're going to need the probability of splitting at each step, right? Feed it, or the probability of splitting. Is that what you use?
No. So if you given a specific, you give me a jet, I construct this tree, and now I'm just trying to build up this hidden representation. So I'm just going to I start out with some seed particle, some seed value for what the hidden representation is. And then the first thing that happened was that these two daughters were created. So I just say, okay, hidden representation updates your sort of prior on now these two daughters exist in my sample. And now I know what the jet is. Now I go to the next time step. These two daughters were added to my sample. Okay, I'll update your prior with these two daughters added. So I never in building the hidden representation, I'm not taking into account how likely one thing was to happen, I just say, this is what actually happened, update your prior.
Okay, so you're not really using like the splitting function at
No.
each step.
I'm just always saying, this is what happened, update your prior. And in practice, how this is very precise. So I have some of my data representation is just really like a 100-dimensional vector of numbers. And there's some W, V, and B, which are just some learned parameters of my model. And I'm just adding in two, so these are just 8 degrees of freedom, like 2 form momenta, and the previous hidden representation. And the dimensions here are such that this makes sense. So you're just doing this matrix multiplication, and there's some activation function that sort of tells the neural network how to update, then reassign the next hidden representation. So once I have this hidden representation, I have this 100-dimensional vector. I just feed this 100-dimensional vector to 3 different networks, the model, PN, P-mother, and P-branch. So this is just some fully connected network. This is sort of vanilla network that you might think about. You just feed this 100-dimensional vector in here, and you get out a binary answer, like should my binary output, like what's it likely to ending or not ending. This hidden representation also goes to like predicting the mother. So there's just some probability of like which particle should be the one next to the splitting. And so like a technical aside, we order these by like energy, and we only like look at the first like T nodes of our outputs network because we only have T particles at times that T. Don't worry too much about that. And then similarly, we feed this to the branching to model like how the splitting should happen. And we also give the branching function the momenta of the mother at the previous time step. So it like knows like how energetic was my mother. If that really affects how the splitting should happen. So sort of more bigger picture. I have these basically like 4 different neural networks. It's one RNN, and then these 3 hidden, these like fully connected networks. So it's all like sort of 4 simple building blocks, but each of them can sort of model arbitrarily functions. And this sort of whole box here is like what we call JUNIPR. So if you now give me a jet, how exactly do I compute p-jet? So again, you start with just the final form momentum, that's what you give me. I construct a tree, and now I step through the tree as I talked about before. And every time step, I like feed in what actually happened for this event. So now at this time step, I did not end. So P not right. I get P not ending out. I know this was the mother that decayed, so I'm feeding the index of that, and I get the probability of that mother actually being the one that decayed. And I know these daughters were created in this jet, so I feed those 2 daughter momenta into P branch, and I can evaluate these. These are now just 3 numbers that comes out. And I just sequentially go through my whole jet, and I multiply all these numbers. That's the thing that's combined to give me P-jet. So there's a quick note on how we train. So this model is very simple. It has like 5,000 parameters in it, which is ridiculously small compared to like most like neural networks you hear about. Like, a lot of neural networks have like 10 million parameters. Like that's like standard in like computer science. So 5,000 is really, really small. And we choose those parameters in such a way that we like maximize the log likelihood on some data set. And in practice, we define those parameters by doing what's called gradient descent.
So how do you construct the data set? That's just from QCD evolution and
So
decays and
so our data set is we have Pythia Monte Carlo generated. So we have 500,000 E plus and minus QQ-bar events. The energy of each jet is about 500 GeV. And we use hemisphere jets. And we use this Cambridge-Hopkins angular ordering. And we don't use any information from the Monte Carlo generator that we like wouldn't have had at LHC. So just like show you, like validate, like what we're doing actually is working. So here I plotted, so I have my data set, and I know exactly, I can construct these trees. And I can look at the theta is the angle between the mother and the soft daughter. So at times the first splitting, all the first splittings of all my trees in my data sets, I histogram what happens. This is what's in this blue histogram. And so what's in pink is the probability distribution that JUNIPR has learned. So there's a very, like a perfect agreement. But as I'm evolving in my jets, the probability over angles is going to change because my tree was angular ordered. So later time steps are going to be small angles. So if you look at the pivot frequency, like histogram in my data sets, it's shifted to smaller angles now, but we still model that probability distribution. So this just convinces you that we have learned these probability distributions really well, and they evolve over time. And we have a lot more validation plots showing like all the PN, P mother, and P branch. But in terms of interest of time, I don't think I'll dwell on these too much unless you have a question.
Yeah.
So okay, so now JUNIPR is trained and it's ready to operate. So just to illustrate, here is a quark jet. I plotted it here. Sort of again, this is the clustering tree. And the energy is this color coded at the bottom. So blue is more energetic and red is more lower energy. And for every node here, I plotted the probability Pn times P mother times P branch. So here at time step 18, you get these three numbers, which is going to combine 10 to the minus 2.8, which is a small number. And then here's the multiplicity is whatever it is, like 20 or something. So you multiply all those things together, you get some really small number as was asked earlier. So the question is, what are these tiny probabilities really good for? So there's like 3 applications we thought about. I'm not sure if I'll have time to talk about all of them, but I want to focus on discrimination. There's also, since we have learned these probability distributions we can generate, and we can do what's called reweighting, and I'll touch on that in the end. Okay, so let's quickly talk about discrimination. So to discriminate, I need 2 things to discriminate. So I have my quark samples, but I'm going to try to discriminate that from boosted Z's. So you have a Z at rest, it gives a quark anti-quark. But Z's are often produced very boosted. So my quark anti-quark are really going to be moving in the same direction, and it's really going to look like a one jet in my detector. So what I really want to do is I want to try to just learn how to discriminate boosted Z's from just quark jets. So I have my 2 data sets, sample of quarks and a sample of Z's, boosted Z's. And so I'm really tightening that window to make it more difficult for ourselves. And I'm going to train one model in each data sample. So it's called PZ and PQ. Now if you give me some history jet, I can evaluate this ratio, PZ over PQ. And if it's more likely to be the probability of it being a Z is a lot bigger than being Q by some amount. It's larger than some threshold. I'm going to tag that as the boosted Z. How does this work in practice? Again, I have this likelihood ratio of Z over Q. If it's larger than the threshold, I'm going to tag it as a Z. So here's this likelihood ratio over this is my quark data set, and this pink is the Z data set. So there's separation here, and by putting some cut, you can create like a similar curve. So again, you sort of, if I want 80% Z acceptance, so I go here until I get 80% of my Z's. The question is, how many quarks are in my sample if I make the cut here? That's what this says. So what's in blue here is the sort of discrimination power we can get with JUNIPR, and the sort of simplest thing you can use is like tau 2-1, and it's a genuineness ratio, plus just multiplicity. These questions are how much better can JUNIPR do? So we can do much better.
So I'm still struggling here to understand. So you have a whole bunch of events.
Yes.
Each final state momentum configuration has a very small probability of a certain clustering sequence and so forth, and those of course differ whether it's a quark or a Z type jet. So what are you using to discriminate? Are you mapping back, or?
So what I'm using to discriminate is this likelihood ratio. So you give me one jet,
Right,
I feed that through each of my models.
right,
So I get PZ and I get PQ. So they're each going to be really small numbers.
right. Then you now have to match it to a given observed event. Or
No,
not.
so that is one event that you pick the events.
Yes,
You
okay,
give me the jet, you give me the events. I don't know what that event was, a quark or a Z,
right,
but you didn't tell me that. So I just feed that through my model, I get these two numbers. And that gives me some number, and so that's what I'm plotting
Seems
here.
very inefficient, though, that's what I'm trying to get at. I mean, how, it's unlikely that if I give you a certain initial momenta, you're going to end up matching the final state. Momenta that
I'm
I
not sure
see.
I understand that.
He's just computing a likelihood ratio, basically.
But based upon what? I mean, you're looking at a final state of, a certain number of particles, a certain momenta. So how do you decide the
So-
likelihood that came from the zero cube?
So this, here I'm plotting the likelihood ratio on the Z data set, that's what you say pink here. And the likelihood of my quark data set, I want to see in blue. So if you just gave me the mixed data set of quarks and Z's,
Yes.
they would just be this double hump Grant diagram you see here. That's what you would see. I guess you would have to add them together, so they'll be a little bit different. But like the sum of these two histograms together is what that mixed data set would look like. And my statement now is if you tell me I want 90% Z acceptance, that's what I want. I then go read off my ROC curve, and I say, okay, 90%, and I see here, okay, I'll need to get like 60% quark reduction in that case. In practice, that means like you're putting a cut like somewhere over here. So that's the
But you input something into this, right?
my input is that I've trained this network on these two labeled data sets. But now if you give me a mystery jet or a mystery data set, I can repeat that process on that mystery data set, assuming that like the underlying physics is the same.
I guess I'm still confused because you still have to take your final states that you see and map it back to either the Z or the quark. And that, I still don't understand how you can do that efficiently.
Maybe we should talk after.
Okay.
I'm not sure if I'm fully understanding your question. But let's, so this is really like my money plot, so I'm happy to like end after this. So my starting point was that I wanted to like pick inside and try to understand what's really happening. So if I here I plotted one quark jet and I've plotted one jet. And I've modeled these probability distributions as a function of different time steps. So every time step I'm just plotting the likelihood ratio of that time step. So it's like 10 of that number. So if this number is very negative, that means that it's very quark-like, and is positive, that means that it's very Z-like. So here, look at the quark jet. So the first time step gives me very negative. The JUNIPR predicts a very quark-like, but this very quark-like. Similarly, this is quark-like. You can look at all different time steps. And you look at the boosted Z, saying this is very Z-like, and similarly, like what these other ones are. So I didn't really put in any physics here. I just I had these two data sets, one with a label quark, one with a label gluons. I modeled them on this sort of QCD-inspired like clustering tree network. And if I now look here and say, okay, as a physicist, trying to understand why does JUNIPR predict this to be very quark-like? Well, if I have an angular ordered tree, it's a quark. The first splitting is just some wide-angle soft radiation. So and JUNIPR has learned that is a very quark-like thing to do. However, if I look at the Z goes to QQ bar. So it's a very sort of energy equal for splitting. And you can see that, so Z is a color singlet, so you can see like all the radiation is like happening in between those two first splittings. And it has learned that is a very Z-like thing to do. So by having these kinds of visualization techniques, we're hoping that we can provide intuition for the energy distribution, because opening angles, multiplicity, branching patterns. We're hoping that we can look at, study these quantitatively and try to get some insight into constructing new calculable observables, in which you can use to construct, distinguish quarks and gluons. Yes.
And one way, I don't know if this might help, but this kind of would help me earlier. I think I understand what you're doing. One way you can think about this is that if you had a much simpler topology, people use these matrix elements methods, right? Where they basically have from theory, they have a model for the probabilities of various outcomes given a model, right? And then they can use that to construct the likelihood. And the point is, for jets, you have no hope of actually using QCD to come up with a matrix element for a probability, or a matrix element for a given jet. But this tree makes a model of that, which is good enough that it gives you discrimination. So you can think of it as a proxy for a matrix element method.
Sure.
Right.
I think what I was missing before is that you're taking the final momenta and you're doing this clustering on that final state, the momenta of this final state. And that gives you a tree, an ordered tree. So the final state is already determining your ordered tree, and then you can do what you say.
Yes. All right. So let me just, I can wrap up in 2 minutes.
This is 2 minutes extra if you need to. We asked a lot of questions.
But just really quickly, I just want to say that we model these probability distributions as the jet evolves. So in principle, just sample from this distributions and generate new looking events. These are just two plots and the flash tubes. Just so I had some data set from Pythia of quark jets, and they had specific mass distribution and multiplicity distribution. And just by having trained my JUNIPR model on this data set, and learned probability distribution, I can sample from those distributions and generate new events. And they have similar characteristics in terms of mass and multiplicity. Similar if you look at the mass versus multiplicity, 2D, very similar looking features. So just very quickly, that's something we can do. Similarly, you can imagine that you have one of these JUNIPR models that's just trained on real LHC data. That as a theorist, I don't have access to real LHC data, but I do have access to imperfect simulations. But sometimes my imperfect simulations might not match what's actually you would see at LHC. So if I train one of these models, I have a JUNIPR model on the LHC data, and I have one model trained on the imperfect simulation data. I can just take my simulated data, and I can just reweight it by this likelihood ratio. I can get my observables in my imperfect simulation to match my LHC. So as a proof of concept, we just took two different values of alpha S and Pythia. So you just focus on the left and this middle column here first. Here's two different values of alpha S. You look at tau 2.1 and tau 3.2, and just the energy distribution versus angle. And you can see that alpha S changes those distributions a little bit. But I can now reweight the pink data set to match the blue data set using JUNIPR, and you get more or less perfect agreements. This concludes. So we have this unsupervised probabilistic model for jets. So this the basic idea was we have this neural network architecture that's sort of scaffolded around this leading order description of physics, and then that's taking a step towards can we pick inside and understand what is making it think that this is a quark versus a gluon. And importantly, this is built in such a way that it can be trained directly on LHC data. And I think there's a lot of future applications that are really exciting. We're currently working on this 3D quark versus Z, which is sort of toy example. We're now working on doing it on real quark versus gluon and have some results if you want to see what's the top QCD discrimination, possible interpret and understand what's happening. I also mentioned this reweighting, and also there are ways of generalizing this. So far I only worked with momenta. I didn't talk about quantum numbers. Maybe you talk about not just jet by jet, but event by event. There's some interest from the heavy ion community using this. I'm I'm not sure if any of you are interested, but all the code is public, so I should push this out to the community. So, all right, thank you for your time.
I don't know if this is an interesting question, but you could imagine maybe using this I mean, one practical problem you sometimes have is just generating enough Monte Carlo for very rare events, right? If somehow these rare events were rare because of a combination of somehow rare splittings, then you could imagine that something like this could do pretty well at, pushing you out onto tails of distributions. You sort of train it on Monte Carlo, and then you can compute the probabilities of very, very rare events.
Mm-hmm.
And to some extent you can just kind of test this, right? Like very high mass. Have you thought about any of that?
I thought about it. I haven't had time to push any in that direction.
Yeah.
Definitely very interesting. A lot of time.
Yeah, we have some new physics which also give jet-like structure, but we don't know what it gives us. If I only know it shouldn't look like a gluon or quark or whatever, double boosted double Z. Does this help us to identify some of these exotic
So
jets?
I am talking to some people now in machine learning terms, we just call it anomaly detection. So you can, of course, just use JUNIPR for anomaly detection. We don't have any results, we're just thinking about it, but there's a whole community in the machine learning, machining for jet physics, people thinking about anomaly detection, ways in which you can sort of automate picking out weird looking events from a data set. So definitely something we're thinking about.
What is unsupervised about this? I mean, my impression was that unsupervised machine learning was where you didn't give it the right answers and it sort of discovered the right answers or made up its own classification. But it seems like here you're just at least the way you described it, it sounded to me like you really are just training it on some data.
So I'd say
does unsupervised mean something different from what I thought, or what?
Unsupervised means that I don't have a sort of truth label at the end. I look at my output of my neural network, and there's no truth labels. So as I sort of said before,
because you don't know the probability.
Exactly. So
it's finding the probabilities.
If you give me a label for every event with some probability, I can construct a neural network that sort of learns that probability, and that would be a supervised way of learning probability. I just say, here's some data, and I'm learning to maximize this sort of probability distribution.
Yeah, but you are, that's, okay, I see.
So
you are sort of,
semantics.
it is kind of, yeah, but you are giving it a bunch of data and saying, find the probability distribution of this data, which is real data, which is in that sense, truth. But it's just because you're finding a probability that you're calling it unsupervised.
Those are the words that people say.
But you only use this full momentum, right? You don't really label what particles you see, right?
So we haven't. So I'm working. We're working with the undergrad at Harvard to add in quantum numbers, specifically charge information, to try to more information is better. That's the general. We try to discriminate.
In general, in jet, you may have the pi zero, which give you photons, or something give you leptons. You haven't used any of these things.
We have not used any of that information. But that is something we are currently working on. So.
There's a much simpler thing. Maybe other things work better. But suppose you were interested in some new physics topology, right? But you didn't want to commit to a specific model with full matrix elements and so on. you could do something like this, right? You could sort of train it to get a probability distribution based on, something like face-based considerations, and have it try to use this log likelihood as a discriminant.
Yeah.
Is that, I don't know, maybe that's,
Don't you have to know where you're starting though? I mean, if you have a new physics model, well then of course you can create a new probability
yeah,
distribution.
you'd have to input the model,
Yeah,
at least
right.
the topology, right?
Yeah, I don't know if that specifically, but there's lots of possibilities.
Yeah.
And in general, I'd say it's like very, very flexible framework, and I think there's like infinite like additions and applications of this. We just have this sort of simple like discrimination example so far, but we are branching out.
So you didn't say anything about factorization. Is it assuming that each particle at the end of the shower produces one hadron? So you identify with, how did you go from the shower to the hadrons?
Well, I don't really talk about the shower. Like I just, I start with the hadronized particles, and I construct a tree, and I sort of loosely say, if I can have my algorithm for constructing a tree is sort of not crazy, that sort of creates like some, and like I'm never really talking about the shower. I just have like a model that looks a lot like a shower, to sort of try to like understand like what is happening. But I'm never actually like I do say a lot of words that sounds like a shower, and that, but I'm always just talking about the tree, and I'm thinking about it as a shower.
I think maybe
That's
he's
super
asking
easy.
more about the first step, like you get, let's say, some particle flow, for one particular jet at the LHC. Then what are your flow momenta that you start with? Do you start with the set of flow momenta of each hadron, or what? I think that's what he's asking, right?
So just formant of each hadron. That's my starting point.
So if you have
Your
a
tree is not really one happen.
Exactly.
Right.
That is
It's just
that's
you
the key.
construct from your final
Yeah.
state.
That's
You're
what I
making
meant.
a
Push
model.
your best guess of what
Yeah,
happened, but
it's
not
modeling
really
it
what
as a
happened.
shower in some sense. It's modeling it as this kind of rough shower.
Yeah.
So if you had an eta decaying to 3 pions or something like that,
Mhm.
then you would still cluster those pions according to your clustering algorithm, and after a step or two you would get back to the eta, but you don't care about the fact that it started with an eta. Right?
I'm not putting in any sort of inputs of what happened at some early time step. I'm just starting with the hadronized formant.
I guess the point is that the shower is an IR safe thing, and so it doesn't in practice probably matter that much, if you, that you're starting with hadrons. I mean, there's a lot of, because you presumably rapidly lose memory of the, well, anyway, I think somehow the fact that a shower is IR safe means that this very, very rough hadronization model, if you like, that one hadron is one prong of the shower actually works okay, right?
Yeah, and I think just sort of generally, I'm just using the fact that like more or less things are like local.
Just leave it on that shit.
I'm just using locality of like I sort of most of the time, if I have two things that are like close together in my detector, they probably came from.
Right.
That's like really the extent in which I'm. What I'm using. But
So I guess what I'm asking, in Pythia, you can have a port and a nearby gluon that are in the shower, and they end up in a single hadron.
mhm.
And the fact that you're fitting Pythia well means that that's a small effect. Saying, going too far.
I'm not sure if I want to read into it that much.
But, you're fitting Pythia with hadronization?
Yeah.
Yeah, so it's not just the shower there, it's kind of, and
Yeah,
Pythia's been tuned to be, I mean, I'm not sure if that comes into it as well.
Well, whenever I like say like, I don't know, like here, like I have some, I say like I have some Pythia data set, and maybe like some things or specifically happens here. Like that is assuming that like I had that set, I set my initial hard interaction to be e plus or minus q bar. But if there was like in the Pythia, like if there was some like there's some gluon radiation and there's some color connection stuff going on, that's already all modeled in Pythia in some way, and I'm just learning the Pythia data set you gave me.
So the fact that this agrees, this demonstrates that this is an efficient description of the data. Is that what I'm supposed to interpret it?
This agreement is just on distribution, and not an event by event agreement.
Yeah,
Right.
this is probably the distribution.
So Pythia has its own ordering. Basically, the one you compile doesn't necessarily match the
Yeah.
But the fact that they agree, is it because this is an efficient description of the data, or they just would have agreed eventually if I trained it with enough parameters? If I had the
I
10
think it's-
billion parameters, it would agree.
It's fair to say it's like inefficient, like it's an over parameterization of the model of the data. Well, that's not. I have 5,000 parameters and I have 500,000 data points.
Sounds efficient.
But like, it's still not the. I don't know. 5,000 parameters is more than Pythia has. Like, I don't know how many parameters Pythia have, but like, it's not the most efficient encoding possible. So I don't know.
But no one understands Pythia except 5 people. Hopefully we could understand, if we read the code, we would understand this.
Well,
Whose code?
This code versus.
You would understand it, or?
I think I can safely say this is simpler than Pythia, but I think Pythia has a lot more I can for it than this has. Pythia is pretty amazing, so doesn't make it easy, but.
So kind of, just a mundane question. Suppose I had a 5-parameter, just a random number function, that I could numerically compute, okay? But, not super efficiently, but I could compute it. Now I want to integrate this function of 5 variables over various domains with various values, or with various values of these input parameters, okay? So, or make it 5, 10, relatively large number of parameters in the function, okay? And so one way I could do it is I could, and then there's a question of how many dimensions is my integral, maybe it's a few dimensional integral or something. But anyway, one way, traditional way I could do this is by Monte Carlo. I could do the integral by Monte Carlo. Right? But another thing I could do is I could try to use something like this to learn the function, right? Like if I often do that if I have a 1 or 2 dimensional function, I'll just figure out some simple fit for the function and use that to do my integrals. And it's often a much, much better way of doing it.
Everything analytically, is that what you're thinking?
Perhaps, but at least efficiently. I mean, the idea is that, Monte Carlo, I'm always, I'm always worried about whether, there's something special about this particular integral, Whereas I can imagine that I could maybe convince myself better that I've maybe not learned the function. Anyway, I'm just wondering, that's a much more mundane application in a sense.
So,
do you know if people try to use machine learning in this way?
there's been 2 papers, to my knowledge, who tried to do some sort of face-based integration with machine learning.
Mm-hmm.
One is from like 4 years ago, and I think, and like one was just like December. Forget the authors. But Christian Bauer was asking me about this same thing. Like if there was like some way of using some simple.
Finding a simpler representation, is this a good simpler representation of complicated functions, maybe more generally?
At least it might be like if let's say I want to do some like phase-space integral over like 6 particles or something like that. That's already like pretty complicated. But if you can somehow like parameterize like the probability of like if this is some like efficient encoding of like sort of probability of like however like that those particles like how behave in like phase space. You can use that for your like doing some sort of importance sampling or something like that.
Right.
I have not explored it, but Christian Bauer was asking me about this, and I think that's an interesting avenue to look into. But there was a paper about something like this from December, November. I don't remember the author, but I can find it to you if you're interested.
Well, if there are no further questions,
Yeah.
thank Anders again.
Generated.